know you're going to be given a reference with all the formulas. You already know this, right?
Yes, sir.
Okay. So I just listed these here, so as we're going through some examples, you can eyeball it and remember, oh, okay, that's what the formula is used for. It's no big thing. So first things first, we know that a transformer is basically what? What is it made of? Yes, two inductors, two coils in close proximity. Like my stick on a lip out like that? Okay. There's something that occurs between what's known as the, what's this coil called that's on the source side? Primary to the secondary coil. What is that phenomenon called due to the expansion and collapse of that magnetic field from the source? What's it called?
Magnetic induction.
Okay, well, mutual inductance. We'll use that term. Mutual inductance. Mutual inductance. That's where what field is created? That electromagnetic field, just like an inductor in itself. Well, if I have one source, AC source, this is what's going on, but as the signal expands, what's happening? The lines of flux are cut across and it's being induced from the primary over to the secondary, isn't it? Mutual inductance, that's what it's called. So as far as how a transformer is constructed, it has to do with ratios. Turns ratio has to do with what, specifically? Turns ratio. Number of what? Number of turns in what? Yeah, so if I got a long piece of wire, I start coiling it, I'm making a coil, and it still has inductive properties, but it concentrates that energy more concentrated. Turns ratio. How many turns in the primary to the turns in the secondary? Basically what it boils down to. It's a ratio. This one's the what? Voltage ratio. These two are equal because it has to do with Lenz's law and Faraday's law and the formula in the inductor's lesson until you didn't have to know. But it has to do with that. When you apply potential to a piece of wire, to a coil of wire, BAM! Based on a number of turns, and that magnetic field that expands collapse is directly proportional to the potential. Keep it layman like that. So these two are equal. This one, the current ratio, is the opposite. And we're going to work out another problem here so you can know, yeah, it is. It's right. I remember now. So, we'll come up and do a problem here later. Let's just move down here. There's some characteristics that we got to know. Cores. How many different types of cores do we talk about? 3. And it's what? Air. Iron. Ferrite. Can we identify the difference? For example, like this one would be a what? Air. There's nothing in between schematically. This one would be a what? Iron. Iron, because I have 2 solid lines, and then what am I missing? And the iron ferrite's dashed lines. Like that. An ideal transformer. Ideal, that's a key term. Ideal transformer is specifically describing what about it? Yeah, the power ratio. That's what it's really talking about, the efficiency. So that lowercase eta, power efficiency or efficiency. So the power of the secondary equals the power of the primary. If it's ideal or perfect, then the efficiency would be 100% or 1, or there's no power loss absolutely whatsoever. But there are some things in a coil of wire, such as, or a transformer itself, that can cause not to have a perfect transformer.
Copper loss.
Yeah, copper loss, because the coil of wire itself has resistivity, so there's opposition already. Damn it. And then the eddy currents and the hysteresis, the leftover residual flux and the leftover magnetism, all these things cause us to not have a perfect transformer. So if you see the word ideal, think perfect, and think about the power ratio. Because this would have to be what? To be 100%. What would the ratio have to be? Yeah, 1 to 1. Now, that we're thinking about power in an ideal transformer, if I were to ask you this, the turns ratio in a transformer is 1 to 5. In an ideal transformer, that is. I have an ideal transformer. Turns ratio is 1 to 5. What is the voltage ratio? Exactly. See the difference? I'm asking you about the voltage ratio to turns ratio. It's still equal, even if it's ideal or not. That's the point. No matter what, if it's perfect, meaning no power loss, the ratio's still equal, don't they? Turns and voltage. So don't get got. That's something you can get got on if you're not thinking about this in the right format. Ideal means perfect, yes. Ideal means I have a 1-to-1 power ratio, meaning there's no power loss. Even if it's not ideal, whether it is or it isn't, the turns and voltage ratio is still equal. Think I've driven that home enough? Yes, no, maybe?
Yes, sir.
Okay. Turn ratio